Hello friends, in continuation with the last lecture, today we are going to talk about the next topic, that is elastic transducers. These are the transducers which converts actually the pressure uh, quantity into the some electrical signal. It is one of the very important transducers in the case of the all kind of the transducers, because we will be always dealing with such a kind of the transducers wherever there is a conversion of the pressure into the some electrical signal. So actually these kind of the transducers converts the pressure into the some mechanical displacement, and furtherly this mechanical displacement will be converted into the electrical signal, and at the end we can have the other succeeding instruments which can be cascaded, so that the whole instrumentation system can be fulfilled one by one. Right. So here, actually, it is consists of the elastic element, and which converts the pressure into the mechanical displacement. And as I said it earlier as well, that it can again laterally convert that mechanical displacement into the electrical signal by using the another kind of the transducer, that is called as the secondary transducer. These transducer, the what we can say, the elastic pressure elements are the primary sensing elements in this case of the in this type of the transducers. Which are the primary sensing elements? Elastic pressure transducer means which senses the firstly the changes happening in the pressure, and that are actually these sensing elements are designed to operate under the pressure gauge by binding, deforming, deflecting, or moving some devices, an amount by which it depends on the pressure changes. So these are the some gauges on which we will just detect the changes happening in the pressure, which is by the maybe binding, deforming, deflecting, moving some devices, and so on and so forth. Right. There are commonly used elastic elements, and few of them are here. That is diaphragm, Burden tube, and the bellows are elements. The diaphragm, as we know that the diaphragm is nothing but तो कान के बीच में जो पर्दा रहता है ना, उसको diaphragm बोलते हैं. Some simplest example, right? So the in the ear we will have the diaphragm inside, so that it will just when the sound get incident on it, it will just try to vibrate about its position, and will get the sensation of the sound, right? So the diaphragm is actually the mechanical pressure transducer that is used to detect the slight changes in the pressure in a process. It is a single disc that is stretched and fastened at its periphery and is exposed to a process. Now, since the process pressure is exerted over a relatively large area, the instrument more sensitive to the smallest changes in the pressures. Means suppose as we know that the if the surface area is larger one, the obviously the force exerted on that is will be requiring the more, and the pressure will be the smaller one. So when we exert the pressure on or the force on the larger area, obviously the uh, that devices or the instrument is more sensitive to the small changes in the pressures. On the other hand, if the small pressure is exerted over the large area, the force will be relatively large area, and causes the diaphragm to flex or the bend. A mechanical device such as a pin, or rod, or the bar is usually connected to the diaphragm, so that the amount of the flex can be measured in order to determine the pressure exerted. Means some very pinpointed pin which has a very sharp edge is used connected to the diaphragm, or else the rod, or else the sometimes bar is used. Right. So we'll see a few of them in this lecture as well. The diaphragms can be in the form of the flat, or the corrugated, or the dished plates are also used. Now the choice depends on us, and also on the strength and the amount of the desired deflection we are requiring in a particular application. The diaphragms are made from the elastic metal alloys such as the stainless steel, phosphor bronze, beryllium copper, leather, Teflon, neoplane, etc. etc. So these are the few examples from which we can make the diaphragms. Okay, and these are the elastic alloys. Alloys, we know that the different metals, if we combine them together to form a particular element or the device, is called as the alloys. Now they are fabricated by pressing, stamping, or the spinning from the sheet stock, or are integrally machined with their supporting wall from a bar. Now here the choice of the material of the diaphragm is based on the consideration of the chemical nature of the fluid. Means actually the choice of these diaphragms depends upon the where we are going to apply them, or the application area is very important one, because we cannot choose such elements which will get corrugated because of the chemical elements we will be using it, or chemical nature of the fluid which is exposed to expected to come in contact with the diaphragm, or as the temperature ranges, because it should not have the temperature effect on it, but the effects of the shocks or the vibrations and the frequency responses requirements are also important while considering the one particular diaphragm in application. Now, natural, as obviously these diaphragms vibrate about its mean position on the changes happening in the pressure. So the frequency or natural frequency of this diaphragm can be expressed by using this expression, that is F is equal to 1 over 2 pi or root of K by M equivalent, right? Where the M equivalent is the mass equivalence and the K is the elastic constant of the diaphragm. The operating frequency of the pressure to be measured must be less than the natural frequency of the diaphragm. Otherwise, there will be the some disturbances will happen in the diaphragm, or it can get damaged permanently. So that our operating frequency must be less than this the natural frequency of the particular diaphragm. Means whatever the which calculated is the maximum frequency we can consider over here, right? Now when the pressure is applied to a diaphragm, it deflects, and the maximum deflection at the center of the diaphragm, y0, can be measured by using the displacement transducer. And for a thin plate, a maximum displacement or deflection y0 is a small, and a linear relationship between the P and Y0 exists. P is the pressure and the Y0 is the deflection or the maximum displacement. So this relation seems to be the linear one if the maximum displacement is small in this case. So this is something like the diaphragm generally we used to have. So this is, we can call it as the diaphragm, and because of the application of the pressure, it will get deflected down in a downward direction, and this deflection from the mean position to the its exterior position. So this displacement is called as the y of 0 displacement or y0 displacement, and there is the reference for the differential pressure on the other side, so that the we will be getting the changes happening in the pressure. Whereas the other example is the membrane diaphragm, where the originally where there is no pressure applied, or as the pressure difference on the both the sides becomes a 0, then this diaphragm or the membrane becomes a straight line. As the pressure getting applied on in the downward direction, obviously inside pressure is lesser than the outside one. If it is considered as the outside pressure, then this will deflect in the downward direction, and that this deflection at the center of the membrane is considered as the maximum displacement, and on the other end where they are the fixed to the wall, the deflection goes on decreasing in path or curvature. Some curvature is there, having some radius r, and the t is the some transverse deflection we can consider here. And now this diaphragm displacement is considered over the y. Or else if the pressure outside pressure is lesser than the inside pressure, then obviously this membrane can be deflected in the upward direction as well. Similarly, by we can have the other quantities remain the same, deflection and all other, and t is the thickness of that diaphragm or the membrane we can consider. Now that maximum displacement at the center is given by this equation. Not necessary to remember this kind of the equations here. So y0 is equal to 3 by 16 root of 1 minus square by et cube r raised to 4. So here the important thing is to remember that the E is the modulus of elasticity of the diaphragm material, and nu is the Poisson's ratio. We've already seen what is meant by the Poisson's ratio. However, the allowable pressure should be less than the which is given by this equation. Maximum pressure is equal to 1.5 times T by R square sigma max. Where sigma max is the safe allowable stress of the material. For a member, for the membrane, the deflection is larger and the relationship between the P and Y0 is a non-linear, as is expressed as a nu is equal to 0.3. Earlier we have seen that the relationship, because for the case of the diaphragm, the deflection is a small one, and the relationship between them P and Y0 is a linear one, but here we will get the non-linear relationship for the membrane, and its Poisson's ratio is 0.3. So the pressure is equal to 3 point, means just substitute the values of the zero point 0.3 over here and try to rewrite the expression. Well, the P is equal to 3.58 ET by RS to 4 Y0. The deflection Y0 is for both the bending and the tension of a flat diaphragm at any deflection, which is given by the expression, that is P R raised to 4 upon ET raised to 4 is equal to, is a polynomial fitting. That's it. Y0 by T is the expression we use, 5.86 Y0 by T plus 3.58 Y0 by T cube. So where Y0 is the deflection diaphragm, T is the thickness of the diaphragm, E is the Young's modulus of the material, R is the average radius of the diaphragm, and P is the pressure one. Yeah, thank you.